Hi, this is Jairus Padiz. In this video, we are going to discuss the laws of probability and how it can be translated into logical laws. Let's start. We're talking about unconditional probability over sentences. We are not talking about what it means for something to have a certain probability. We are not talking about how certain probabilities are generated. We are not talking about the probability of sets or conditional probabilities. We are talking about what we can validly deduce given certain probabilities. We're talking about laws of logic, just like other laws of modus ponens. It doesn't tell us if P is true or if P implies Q is true. It doesn't tell us what these statements mean. What it does tell us if given P and given P implies Q, we're allowed by the laws of logic to include Q. That's what we're looking at here. We're going to introduce a notation of the probability of a certain statement S is gonna be written as P of S. What's going to come out is not a true or false, but a numeric value. There's gonna be parameters in that value. The first rule is the probability range principle. It says that for all S, the probability of S is between 0 and 1 inclusive. I'm going to represent that as P1 or the probability range. This should make sense. We understand probability as a number between 0 and 1 inclusive. It wouldn't make sense for us to have a negative probability and the probability greater than 1. Next, we have the probability tautology principle. That is, for all laws of logic, the probability of that law of logic is equal to 1. I'm using L to represent the logic truths here. For all logical truths, L, the probability of L is equal to 1. I'm gonna represent P tout or the probability tautology principle. It makes some intuitive sense. If you think laws of logic are true in all possible worlds, then there is no chance that the law of logic could be false. So the probability of every law of logic has to be 1. Finally, the principle of finite additivity. For all statements S and R, if it's not the case that S and R, that implies that the probability of S or R is equal to the probability of S plus the probability of R. In other words, for all statements S and R, if it is not the case that S and R, then the probability of S or R is equal to the sum of the probability of S and the probability of R. I'm going to represent that with PF add or the principle of finite additivity. To understand a little bit more, let's have an example. Let's assign two separate coin flips to S and R. This would be the reason that you need to be the case that S and R can happen at the same time for this to work. What is the probability of S or R? What is the probability of either the coin on the left flipping heads or the coin on the right flipping heads? We have 3/4. 3 of the possible outcome includes at least one head. Only one of the 4 includes 2 tails, so 3/4 is the probability. However, the probability of S is one coin flipping heads, plus the probability of R is the other flipping heads is actually gonna be 1. So if it's possible, or if S and R can both happen, then in fact this statement is not going to be true. However, if we do have something that is mutually exclusive probability, let's take the idea of rolling a dice. If you're saying that S, the dice will come up at 5, and R, the dice will come up at 6, there's no way that the dice will both come up a 5 and a 6 in a single row. So the probability of either a 5 or a 6 is equal to the probability of it being a 5 plus the probability of being a 6. The probability of rolling either a 5 or a 6 is 2/6 or 1/3. And the probability of rolling a 5 is 1/6 and the probability of rolling a 6 is 1/6. 1/6 plus 1/6 is 1/3. Hopefully that makes sense. With just three principles, we can actually prove some fundamentals of probability. This is going to be the sum of the probabilities of S, and not S is 1. If you have the probability of not S and the probability of S together, either S or not S is a certain, it's a law of logic. We're going to prove it. The conclusion that we're trying to get is the probability of not S plus the probability of S is equal to 1. First, we have our probability tautology principle universal instantiation. The probability of S or not S is equal to 1. Then we have our principle of finite additivity universal instantiation. It's not the case that S and not S implies the probability of S or not S is equal to the probability of S plus the probability of not S. Then we go ahead. It's not the case that S and not S law of non-contradiction, which allows us to use the modus ponens on P4 to get the probability of S or not S is equal to the probability of S plus the probability of not S. Therefore, using the law of identity in 1 and 4, we can replace the probability of S or not S equals 1 to get 1 is equal to the probability of S plus the probability of not S. Using identity, we get the probability of not S plus probability of S is equal to 1. Thus, we have proven our rule of probability. That's Thanks for watching.